right, welcome back to our investigation of sequences and series. Today we're going to take a look at a really cool specific kind of series called a geometric series. So recall that we looked at this particular series before where we add up the successive fractions where we kind of cut it in half every time. We looked at this in the context of that unit box, right, where we had the box that had area 1 and we cut it in half over and over and over again, and we could express the area of that box as this infinite sum of these fractions. One way to look at the terms of this particular series is that each term you can multiply by 1/2 to get to the next term. And then that term, you multiply by 1/2 to get to the next term. And so the terms of this infinite series have what's called a common ratio. And in this case, that common ratio is 1/2. Having a common ratio is the defining characteristic of what we call geometric series. So today, we're going to investigate how we can kind of work with and manipulate series that have a common ratio that we call geometric series. So again, reminding you that we looked at that unit box, so that box that had area 1, and that's one way to kind of visualize why this series might converge to 1. So what I'd like you to think about is pause the video and think about what would we expect to happen if instead of starting at n equals 1, we started the index at n equals 0. So go ahead and pause the video and write down what you think this sum would converge to in this case. So my conjecture is that this sum will now converge to 2, because by starting the index at 0, what we've done is we've said this series now, when n equals 0, 1/2 to the 0 starts at 1. But it's still a geometric series, so we get the successive terms by multiplying by 1/2, and then multiplying by 1/2 again, and so on. And so we see that this series is the series we were looking at before, where the index starts at 1, and we know that converges to 1, and so we've really only just added 1 onto the beginning of that series. Okay, so that's my conjecture about what this series is going to converge to. And what we mean by that when we say a series converges is that when we look at the partial sums, so instead of going off to infinity, we just go off to some number like 10 or maybe 50, or in general we might put just a k or something up there. And what we say is that as we look at larger and larger partial sums, right, like we do more and more terms, those partial sums get as close to 2 as you could want. So that's what we mean by a series converging. And so what I want to show you is how we can take advantage of this geometric structure, this common ratio, to calculate a specific partial sum that would take a long time to try to do by hand. Okay, so in particular, we'll do one that's not too long, but still it wouldn't be fun to try to do this by hand, because each of these fractions is actually going to have a different denominator, so it would be a pain to do this. But because of the geometric structure, we can do some fun algebra things. And in particular, what I want you to think about is what would happen to this series, this finite series, this partial sum, if we multiplied it by that common ratio again. So here's what's going to happen if we multiply that by its common ratio. And what you'll notice is that all of these middle terms get repeated, right? Because we get from one term to the next by multiplying by the common ratio. So what's going to happen if we subtract them? Well, think about it this way. If we write down the subtraction, well, we're going to have this 1 here. That doesn't get canceled, but 1/2 and minus 1/2 are going to cancel. 1/2 squared, those are going to cancel. There's going to be a 1/2 to the third here that's going to cancel that one, and on and on and on, and that one's going to get canceled too. So the only things we're going to have left are this last term and this very first term. All the other middle terms are repeated, so when we subtract, they're going to get canceled. And so now we can simplify this algebraically, right? We have s sub 10, which is some unknown sum, and then we have whatever s sub 10 is minus half of s sub 10. So we can, and the other thing we can notice here is that I left this as 10 plus 1 because there's some nice canceling that's going to happen to help us simplify that. So what I'm going to do is I'm going to factor a 1/2 out of each of these. So this exponent's going to go down to 10, and we're going to simplify the left-hand side. So we get 1/2 of this mystery sum is equal to the 1/2 that I pulled out. And now this expression is 2 minus 1/2 to the 10. And the only reason I did that is because now these halves are going to cancel, right? I want to isolate s sub 10. That's what I'm interested in calculating. So I'm going to multiply both sides by 2. And we arrive at 2 minus 1/2 to the 10th, which is about 1.9990. And that's the partial sum. So we didn't have to add up 10 fractions and find a common denominator. Because of the geometric series structure, we could actually come up with a little shorthand way of calculating it. And now I want you to notice there's nothing really special about the fact that we were working with the 10th partial sum. We could just as easily have looked at the kth partial sum and gotten kind of an analogous result. So let's take a look at what that looks like. So instead of 10, I'm just going to put the letter k. And now we can ask ourselves, what happens to this expression as k goes to infinity? Because it looks like, if we did our algebra right, that we could calculate any partial sum. All right, so what we're going to do is I've got this link to a blank Desmos, and we're going to go hop over to Desmos and give this a try. See if we can figure out what's happening with this formula we have for the partial sum. So what I'm going to do is I'm going to make this look at the sum. Okay, so we're going to start at 0 and we're going to go up to some unknown k, and we're going to take 1/2 and we're going to raise it to that n power. So that's the series that we're kind of investigating. And what we found, and we only want these to be whole numbers, so we'll say k goes from 1 to, I don't know, let's just say 40 by 1s. And what we think is that the partial sums can be expressed as 2 minus, what do we say, 1/2 to the k, right? And so right now when k is 1, certainly that means n is going to go from 0 to 1. And so we're going to be summing up the first two terms of this series, which will be 1.5. And so what I wanted to show you was that this is giving us the same value. So this quantity that we calculated, s sub k, really does give us the partial sum for any k that we want. And so now the question is, well, what happens to that quantity as k goes off to infinity? And hopefully you can see the decimals are getting awfully close to 2. And in fact, once we get up past 36, 37, 38, now the computer, it can't tell the difference between 2 and our number once we get to 38. The decimal places it keeps track of are not enough to tell the difference. And another way to think about that is just looking at this term, right? When we take 1/2 and we raise it to an exponent, this number 1/2 is smaller than 1. And so what happens is, as we raise it to higher and higher powers, numbers that are smaller than 1 actually get smaller and smaller and smaller the higher power you raise them to. And so this term by itself, this 1/2 to the k, that is going toward 0 as k gets bigger and bigger and bigger. And so basically we're subtracting something from 2, but that something we're subtracting is going to 0. So eventually our partial sums approach 2. And as we see here, once we get past 37, the number of digits that they're the same as 2 is really, really, really close. Okay? So let's flip back to the slides. So this confirms our intuition that the series should approach 2, and we did that by analyzing the partial sums, which we were able to kind of play with because of that nice geometric structure. Okay? So what I would like you to do is to, given this sum, I'd like you to try to figure out what the pattern is and find a way to calculate the sum of just the first 18 terms. All right? So go ahead and pause the video and see if you can find this sum. All right, so how are we going to do this? Well, since this is the geometric series video, that's kind of a clue that this is probably a geometric series. So what we're going to try to do is find out what's this common ratio. What am I multiplying by to get from one term to the next? And we'll see if we can take advantage of that to find the sum that we're interested in. Right? And so, and also I put a question mark here because like we want to sum 18 terms. What is that 18th term going to look like? It isn't obvious at first, but once you see this pattern, right, the common ratio looks like it's a half. That 7 stays the same in the top, and then we multiply by a half each time. And so we can express the sum above. This is the same thing as saying 7/8 times 1/2 to the 0. That's just 1. This term just is 1. And then we're going to stop when we get 18 terms. And so that's going to happen when we are looking at 7/8 times 1/2 to the 17 power, because that will make 18 terms altogether. All right. So now we're going to try to use, similar to what we did in the previous example, try to use this common ratio to help us calculate this without having to do this the long way. And so what you'll notice is that every term has a 7/8 in it, so I can factor that out. And what's left is actually that same sum that we were just looking at, right? We're looking at 1 plus a half plus a fourth and so on up to what turns out to be, in this case, 17. And so we can use the formula for the partial sum that we just put together. And so we are going to be looking at 7/8 times 2 minus 1/2 to the 17th. That's the formula we just found for that particular, the partial sums for that series. And if we simplify that down, we get approximately 1.74999 is the sum of the first 18 terms of this pattern that's up here. Okay? And we can do that pretty quickly because of this geometric series structure. So now I want to look at a slightly different kind of example. And what I would like you to do is once again pause the video. I'll tell you when to pause the video, but I would like you to try to figure out what this sum converges to if you can. What does it seem like these partial sums are going to get close to? So there's 2 pieces of advice that I have. One is that determining the common ratio is key. And the way to do that, when you're given a series, I would recommend against just playing algebraically with the summation notation. I would say write out the first few terms until you see what the pattern is. And you determine the common ratio that way and get going. So now I would like you to pause the video and give this one a try. Okay, so writing out the first few terms, we get 2/9 when k is equal to 1, and then it gets 4/27 and 8/81. And so what it looks like is that we have a common ratio of 2/3. So every time we multiply by 2/3 to get from one term to the next. And what you should notice again is that we actually have this common term 2/9 to everything. And so we can factor that out. And now we have a new series that we haven't played with before, but it is a very standard geometric series. It's just it's going to be 2/3 raised to some power, right? We're going to just multiply by 2/3 over and over again. So in order to figure out what these partial sums are approaching, let's look at the nth partial sum of just this geometric part. And we'll come back and worry about the 2/9 in a minute. But we want to focus on that geometric series in parentheses and see if we can find a pattern in how those partial sums are behaving. Okay? So I just wrote out the nth partial sum here. And what we're going to do is very similar to what we did with the series that had a common ratio of 1/2. You'll notice that I can multiply by that common ratio and subtract. And again, all those middle terms are going to cancel. And I'm going to be left with just the new last term and that first one. Okay, when I look at that subtraction. Now I'm going to simplify this one a little bit differently because I want to kind of keep track of some of the pieces a little bit more. So rather than simplify this on the left-hand side, I'm going to actually factor out s sub n. Okay, and on the right-hand side, I think we're going to leave it alone. Let's take a look. Okay, so now to isolate s sub n, I can divide by 1 minus 2/3. And so I get a formula here for the partial sums of this geometric series. So once again, what that means is I can plug in any value for n, and that will tell me what adding up those first terms will be. Okay. Now I can simplify this a little bit more because 1 minus 2/3 is 1/3, and so dividing by 1/3 is the same as multiplying by 3. Now the question is, what happens to this sequence of partial sums as n gets bigger and bigger, right? As we look at successively more terms in the partial sums. And again, we have a number that's smaller than 1 that we're raising to bigger and bigger powers. And so that thing by itself is going to go to 0. And so this whole expression is going to approach 3 as n goes off to infinity. Okay? So let's take that back. We know that the partial sums of this series, where we're the geometric series with a common ratio of 2/3, is going to keep doing this. It's going to approach 3. So going back to the problem at hand, what is this series converging to? Well, it's the same thing. It's just multiplied by 2/9. And so the sum that it's going to converge to should be 2/3. Okay. And what I want to do is, again, we're going to check this in Desmos in just a minute to verify our calculations. But first, what I would like us to do now is, now that we've looked at a couple of these and we've kind of seen how this algebra works with geometric series, how can we use that to maybe do this in general for a geometric series? So I'd like you now to look back over those examples and see if you can think about how to extend that pattern to general geometric series. Okay? So go ahead and pause the video, look back at those problems, and think about how we could generalize what we've done so far. So one way to do that is to, instead of looking at specific numbers, we're just going to use some geometric series, and the defining characteristic is that it has a common ratio, which we're going to call little r. Okay? So we start with some term, a is some constant, and we're going to multiply by r successively to generate this geometric series. And here I've written down the kth partial sum, but we want to imagine like the infinite sum is the one we're interested in. But we're going to look at that by looking at just these finite sums. So we can write the kth partial sum in this way, and we're going to do the same thing that we did on the previous problems, in the sense that we're going to look at what happens when we multiply by that common ratio and then subtract. And so hopefully this is starting to look a little bit familiar. Again, all of these middle terms are going to cancel because they're repeated. Right? So we're just going to be left with this last term, a times r to the k plus 1, and then the initial a when we subtract. And like we did on the last one, we can actually factor out that s sub k, divide by 1 minus r. And now for any geometric series, we get a formula for the kth partial sum. And you can use that on any problem with geometric series where you want to calculate the kth partial sum. Now you just want to be careful about figuring out what that first term is, right? That a term that we're initially multiplying by r, and then just double check the indices here to make sure that whatever you're plugging in for k plus 1 is calculating the correct partial sum. Right, so start off with S1 and S2 and S3 and make sure that you're getting the indices right to match them up. That's the only thing that can be a little bit confusing. Okay, so we have now a formula for the kth partial sum of any geometric series. So the next question is, what happens to this expression as k goes to infinity? right? As it gets larger and larger and larger without bound. So the only thing that depends on k is this term here, right? And so what we want to think about is, well, what happens when I take some number r and I raise it to bigger and bigger and bigger powers? And hopefully you know that if r has a magnitude that's bigger than or equal to 1, this is going to blow up, right? If you take 1, you're going to just get 0 here, which is problematic. So we're not going to think about that case. Geometric series with a common ratio of 1 is going to go off to infinity, because that just means you're adding up the same number over and over and over again. So 1 is right out. But if you plug in something bigger than 1 here, and you raise it to bigger and bigger powers, it's just going to grow, right? It's going to grow exponentially. And so that kind of a sum can never converge, because the terms that we're adding are just going to be getting bigger and bigger and bigger and bigger. But if we use a common ratio that's strictly smaller than 1 in absolute value, then as we raise that to bigger and bigger powers, we are going to get something that goes to 0. So if r is less than 1 in absolute value, then this term is going to go to 0. So in summary, if the absolute value of the common ratio is less than 1, then this is going to be a formula for our whole series. Like the entire series will converge to this value. That's what the limit of the partial sums is. And one way that I remember that is a is always just whatever the first term of the series is, and then the rest of the series will converge to 1 over 1 minus whatever the common ratio is. So we call the first term a, and we call the common ratio little r, generally, when we use these formulas. So that's what that means. Okay. So now I want to go, now that we have this result, let's take a look again at that geometric series we were looking at that was like 4 to the k over 2 over 3 to the k plus 1. So we'll be patient while this loads. Okay. And what we see here is the sum that I mentioned. And what we're going to do is we're going to plot this. So it starts at k equals 1. And we're just looking at the nth partial sum here, right? And this y value is the formula that we just calculated for the sum of the geometric series. So we have the first term, which is 2/9, times 1 over 1 minus the common ratio, which is 2/3. And we conjecture that this series will converge to 2/3, right? So what we're going to do is we're going to look at n going off to infinity and just kind of visually verify that that's actually what's happening. And so what you can see is that the partial sums we're looking at certainly do appear to be approaching that red line. And by the time we get up to 27, it's hard to tell the difference, right? And so this is just serving to kind of give hopefully some validity to this calculation that we've been doing, right? That the sum actually does equal this value as the limit of the partial sums. Okay. And another reason I wanted to share this with you is you can put whatever series you want in here, and this will let you kind of investigate how that series behaves visually with the graph and the dots, how the partial sums behave. Okay, as you change that value. And then you can guess what you think the sum converges to by messing with this y with whatever series you want. Okay, so that's part of why I wanted to show this interactive Desmos thing to you. All right, and that about does it for geometric series. So just in summary, what we say is a geometric series is any series where the successive terms are generated using a common ratio. We call it little r. And in the case when r is less than 1 in absolute value, the geometric series will converge to a finite number. And if r is not less than 1, then it will diverge. So we're not really interested in those kinds of series. And what the series converges to, this is really cool, we can actually calculate pretty easily. That concludes our investigative geometric series. This should give you enough to kind of have the tools you need to play with the homework. And if you have any other questions, please feel free to let me know. I'd be happy to dive in. This also concludes our investigation of series and sequences in general. So just as a summary now, I want to remind you of some of the Taylor series that we looked at. Well, we looked at Taylor polynomials. And what I want to draw your attention to here is that one of the ones we looked at was the Taylor series, the Taylor polynomial for 1 over 1 minus x. This is actually a geometric series where the common ratio is x. And so one of the questions we asked earlier at the beginning of this investigation of infinite sums was, for what values of x does this make sense? Right? Like, we can use this polynomial to approximate this function, but when are we allowed to do that? Like, for what x's is that going to work? And so now we have the tools to answer that. This is a geometric series, so it's only going to make sense to use this polynomial to approximate this function when x is between -1 and 1, strictly between. Otherwise, this series will not converge because it's a geometric series. And just in summary, some of the other Taylor polynomials that we looked at, we can write in summation notation now that we have that tool. And it turns out that most of these basic ones that we're interested in actually converge for all real numbers. And that's because we're dividing by this factorial term, which is going to grow, it turns out, much faster than the exponent will in the numerator. Okay? So this is just meant to be a summary of some of the Taylor polynomials we looked at written in series form using summation notation. These are kind of the big ones to know. The only geometric ones are, the only geometric one is the first one, but some of these are related. And that concludes our investigation of sequences, infinite series, and Taylor polynomials. This is the last of the material that's going to appear on our final exam this time. So thanks for coming with me on this journey. I hope you had a little bit of fun at least and learned some interesting things. And again, if you have questions or like me to go into more depth on anything, please let me know.